You know, in science, we like to tell people that we know what we're doing. And I suppose that's true for a lot of other things. But we like to tell people that we're really on the ball, we follow the scientific method, we have a hypothesis, and all that other stuff. But the truth of the matter is, all kinds of really important discoveries were actually made by accident. I'll tell you about one at the end of the video. Until then, percent composition by mass, which sounds kind of big, sounds kind of complicated. It's actually quite simple. So here we go. It's all about trying to figure out the chemical formula. It's all about trying to know what is in the compound that we have. Let's say we're somehow able to identify the types of atoms. We still need to know how many there are. Now, the first step that we're going to use in getting to that, in figuring out what the chemical formula is percent composition by mass. Now, some things we know that are going to be helpful to us. Number one is that the chemical formula is the ratio of numbers. Now, we know that for us, numbers is often going to be moles, but the chemical formula is a ratio of numbers in an atom. Also, and here's an example, so there's 2 atoms of hydrogen, 1 atom of oxygen, or 2 moles of hydrogen, 1 mole of oxygen, and just to give you another one there. We also can't count individual atoms. Now, if you wrote down the first thing, you don't need to write that down because, well, it's kind of obvious and it's really not that helpful. And then lastly, even when we start counting these larger units called moles, we still can't grab a bunch of those atoms, remember that Avogadro's number, and count them. We always use mass, molar mass, in fact, to bridge that gap between the numbers and the masses. Take a bit of a side trip because what we're doing with percent composition is something we do all the time. We do percentages all the time. You don't need to write this down. I'm not even going to necessarily figure out the whole thing, but if you got a test back and it said 36 out of 44, one of the first things you would do is grab your calculator and figure out your percent. Now, whether or not you do this times 100 part in the calculator or just in your head, right? Maybe it comes out to 0.82 and you just know what it means, 82%. What you're doing with a percent is figuring out a ratio of 100. Again, don't really need to write this down. This is trying to get our heads in the math so we can take math that we know and use it in chemistry. So percent is always a ratio. So what we're working toward is going to be a ratio. And because we're talking about percentages, it's going to be ratios out of 100. Another way we could figure it out is this, right? And you've seen ratios like this in math before where we take 2 numbers that we know and then we're trying to figure out this one out of 100. Sometimes it's out of something else, but for us right now it's going to be out of 100. And if you look at these two, you would see that, hey, if I solve for x, what am I going to do? Well, I'm going to multiply 100 across, so we'll end up making those two things exactly the same. All right, we do percentages in other places as well, other than just tests. Continuing our side trip, so still don't need to write this down. Let's say you had a bag of jelly beans, and you knew the masses of each piece, each color of the jelly bean that you have in there. So 16 grams of red, 28 grams of orange, 12 grams of yellow. Calculate the percent composition by mass. We probably wouldn't call it that, but this is now going to be the language that we're going to see when we move into the chemistry. So I've got a bag of jelly beans that contains different components, and I know the masses of each component. And I want to know the percent of the total mass that each piece makes. Okay, so the first thing I need to do is find that total mass. So take my red, orange, yellow jelly beans, add up the total masses, I get 56 grams. So then the percent that is going to be, I'm going to use orange, is the mass that was orange divided by the total mass of all of them put together and then multiply by 100. Now this is actually quite similar to a test because with the test you take the piece that you got right, the 36, divided by the total that was available, 44, and then you calculate that as a ratio out of 100. So if I had 100 jelly beans, this mass would be the orange ones. And in our case, we're not really going to work out the number, but this is what it would look like. All right, let's go back to chemistry now. This is where we're going to start to see things that look a little bit unfamiliar, but the math is actually exactly the same that we did with the jelly beans, and actually the same thing we did with the test. So this is where we want to start keeping track of what's happening. Now, if you look at this question, it looks a little bit like the jelly bean question. Now, the numbers are a little bit less convenient. Decimals. We don't really like decimals. And we're not going to eat that stuff. But in terms of what we're trying to do, it's the same thing. I've got a compound, not a bag of jelly beans, but I've got a compound that is made up of different atoms, and each atom has its own, each kind of atom, I should say, has its own mass. So what do? I do the same thing. I'm going to find the total mass, 8.78 grams. To find the mass of sodium, that of course is the chemical symbol for sodium, I'm going to take the mass of sodium divided by the total mass, just like I did with the jelly beans. Multiply by 100 to keep the math working out properly, and in this case I end up with a little over 39%. Now I'm not going to do the chlorine, but I could. And the chlorine, of course, would be the mass of chlorine, 5.33, divided by the total mass, same total mass. Multiply by 100 to keep the math working out properly. Try another one. It's kind of the same idea, except a little bit bigger. Now I've got 3 types of atoms, just like I had 3 types of jelly beans. I've got a mass of one, mass of the other, mass of the third. Question is asking the same thing, percent composition by mass. Find the mass of sodium. Now I calculated the total mass without writing that down specifically, but add up all of these numbers, add up the given masses in the question to find the total mass. Then it's the mass of each piece divided by the total, just like a test. The mass of the piece that I got right divided by the total. The mass of percent rather of orange jelly beans. The mass of the orange piece divided by the total mass. And I get 28.4%. Okay, the other ones, hopefully you try those on your own just to confirm if you have a calculator with you or use the one on your computer. And then finally, the percentage of oxygen. Okay, now if you were to add up these percentages, you had better get 100%. And we would expect to be so because those are the atoms, the types of atoms that make up the total, the 100%. What if I know a chemical formula? What if I am given a chemical formula and I'm asked to figure out how do the masses break down in that, because that's going to happen as well. So here's a possibility. We probably haven't done the nomenclature of this, so I can't tell you it's zinc sulfate, but this compound here is zinc and sulfur and oxygen. Well, I'm actually going to do the same thing. I'm going to need the total mass, and I'm going to need the mass that is contributed or the mass that zinc contributes. Well, how do I do that? Well, the molar mass, so if I took this as one particle or 1 mole is more realistic, the molar mass of that would be the mass of zinc, the mass of sulfur, and 4 masses of oxygen. I get those numbers from the periodic table, so we have 65.4 for zinc, 32.1 for sulfur, and 4 times 16 for oxygen. Total mass, molar mass, total mass, 161.5. So then the mass of zinc, if I wanted the percent of zinc, the mass of zinc would be, or the percent of zinc rather, would be the mass of zinc divided by the total mass, just like the jelly beans, just like everything else we've done so far. The only difference with this question to the other one is I have a chemical formula to lead me to masses rather than being told masses in the previous one. But it's really doing the same thing every single time. We're going to do a lab. We're going to do a lab very, very soon after you're finished watching this. And in that lab, we're going to calculate a percent composition. So one of the things I want to do right now is take you through sort of the big idea of the lab. And we'll take care of the details in class. We'll set up what the experiment's going to look like and the actual data you're going to collect and how you're going to calculate the numbers from that data. But what I want you to do is I want you to be thinking about the big picture, what's going to happen in this lab. We're going to be calculating or experimentally determining the percent composition by mass of magnesium oxide. And we're actually going to have 2 directions for this. We're going to have a theoretical direction and an experimental one. Okay, and if you have your textbook with you, it's on page 180 and following. And if you don't have your textbook, well, I'm going to take you through the big picture of it now, and then we'll take care of some of the details in class. We're going to do this. We're going to come up with an experimental percent composition, which means we're going to measure the mass of magnesium, we're going to have the mass of oxygen, we're going to have the mass of the total compound, the magnesium oxide, and we will do our percent calculations. We're going to be able to directly measure the mass of magnesium. Magnesium is a solid. We can put that on a balance. The compound, which of course is magnesium oxide, is another solid. We can put that on the balance. The oxygen is a gas. We can't put that on the balance. So we're going to have to measure that indirectly. And we'll talk about how we do that in class, but again, you can probably guess how we're going to pull that one off. And then we're going to compare it with theoretical. And my theoretical is going to be based on what we saw a second ago. If I know the chemical formula for magnesium oxide is this, then I could come up with the total mass of that, and the mass of the magnesium piece, and the mass of the oxygen piece. And for that, we're using the chemical formula that we expect as magnesium oxide. Here's some sample data. Okay, so your data table is going to look like this. On the top are 3 things that we are actually going to be able to measure. So I'm just going to label the 1, 2, 3. I'm going to be able to put these things on the balance and directly measure them. Now it says crucible and lid. The reality is, when you're doing chemistry for real, you need containers, and those containers have mass. I don't want to include the mass of the crucible and lid, the container, in my final calculation. So you'll notice down here, I'm measuring the crucible lid magnesium, I'm measuring the crucible lid and the magnesium oxide, same crucible and lid every single time, but what I'm after is just the mass of magnesium, just the mass of the oxygen, just the mass of magnesium oxide. I'm going to end up subtracting out the mass of the crucible and lid, the container. Don't really need that. I have to use it in the lab, but I don't want it in my calculation. After that, it's a straightforward example, a straightforward case of comparing those two, get rid of the container, those two, get rid of the container again, and then actually comparing these two, because the difference between the magnesium and the magnesium oxide is the added oxygen. In 1976, there were some British researchers that were studying sucrose, which is table sugar, and they were doing reactions with it and looking at the properties of the final products. The lead researcher told his student helper to get a sample of one for testing. Now, being a student, he wasn't the world's greatest listener, and he thought the boss told him to get a sample for tasting. So he tried it, he tasted the compound, and it turned out to be fantastically sweet. And right away, they knew that they might be onto something, so they did some tests, and so on and so forth, and as the rest, as we say, is marketing. But they ended up discovering and then marketing the compound, this artificial sweetener we know as Splenda. And the other name for that is sucralose. So if you ever see sucralose or Splenda on a food label as the artificial sweetener, non-caloric sweetener, no calories in it, that stuff was discovered completely by accident by somebody who really wasn't very good with English. They meant to be testing, they started tasting. We'll talk to you in class. See you later.